But today we'll be looking about, I guess, just life more generally, looking at kind of marine plankton and its kind of its products, things ultimately those marine snow that you were seeing in the vampire squid video, how that affects or is affected by the gases in the ocean. Okay, so the gases in the ocean predominantly reflect the gases in the atmosphere. Okay, so if you'd have looked at the introductory video, there's this concept that there's a constant exchange between the atmosphere and the ocean, so-called Henry's law, where if you have a high concentration of gas in the atmosphere, a high partial pressure of that gas, sometimes referred to, then that will cause that gas to dissolve into the liquid, in this case water. Now those solubilities are not only different for different gases, but they do change with environmental conditions. Okay, so this exchange, I guess first of all it's very important to point out, it only happens at the surface of the ocean, because that's where it's in contact with the atmosphere. It's kind of obvious, but it does need pointing out. And then once it gets into the ocean, then kind of stuff and chemistry can happen with that. And we can see a hint of that in the concentrations that we find. So if we look at, say, the concentration of, say, of nitrogen in the atmosphere, it's kind of almost 80%. And if we look at all of the dissolved gases in the ocean, we can see that actually, yeah, so nitrogen is still the most abundant dissolved gas in the ocean. But it's a little bit less. Okay, that's because it's not as soluble as some of the other gases. If we look at, say, for instance, oxygen is maybe a little bit more soluble, so we can get a little bit more of it into the seawater. And carbon dioxide is even more soluble. Okay, so carbon dioxide is very, very low concentration in the atmosphere, but actually it makes up a significant component of what's in the ocean. So I should just point out at this point that actually in the ocean now we're no longer talking about just carbon dioxide in this case. So unlike nitrogen and oxygen, which kind of just dissolve in the ocean, so they're still kind of essentially molecules of nitrogen or oxygen gas that are kind of like moving around in between these clusters of water molecules. Carbon dioxide is different in that there's a series of chemical reactions that go on that convert the carbon dioxide, once it's dissolved, into different forms of inorganic carbon. And that's one of the things that we're going to be looking at today. So it forms them into different forms of inorganic carbon that are not gases, so therefore they can't exchange back up with the atmosphere, which is why we can basically store lots and lots of carbon in the ocean, because if only a small fraction of the total carbon dissolved in the ocean is able to exchange with the atmosphere, then that means that the atmospheric concentration can be kind of low, kind of relatively low, but the concentration of the total carbon in the ocean can be very high, because only a small part of it can leak out into the atmosphere. And we'll look at that in a little bit more detail. So again, there's this concept of with different temperatures. So as we increase the temperature, the amount of any gas that we can dissolve in the ocean kind of goes down. Okay, so we have lower solubility than we have at cold temperatures. So that's the thing to think about. And actually also, because we're dealing with seawater, those added salts in the water also have an effect on the ability of the water to hold those gases. So it actually reduces it a little bit. So just as a schematic of the ocean, we have this exchange of gas between the atmosphere and the ocean, and over time, okay, that will reach some equilibrium, so we're at that saturation concentration. But there are these processes that happen in the surface ocean that might affect the concentration of gases. So if we start doing some photosynthesis, that might affect the amount of oxygen and the amount of carbon dioxide in that surface layer of the ocean, which will then affect, again, the concentration in the atmosphere, because the two are linked. Now, this effect to the atmospheric concentration is not necessarily instantaneous, because it might take quite a long time for all of the gas in this surface layer to diffuse up and equilibrate with the atmosphere. So this process is greatly enhanced by where we basically are mixing together the atmosphere and ocean. When we break waves, we form bubbles in the ocean. That basically speeds up this process of equilibration in the atmosphere. But the really important thing about the ocean is that it's quite well stratified. So it has a surface layer, which is quite buoyant, which sits across a deep layer in the ocean. And that means that if we can get any of the gases down into this deep layer from the surface layer, they're isolated away from the atmosphere. Okay, so this is really important for the carbon cycle particularly, because if we can take carbon dioxide out of the atmosphere and move it down into the deep ocean, okay, through this process of the biological pump, that gas is locked away from the atmosphere and can't exchange back up with the atmosphere again. Okay? So those are the major fluxes into and out of the ocean. There are also exchanges of gases through volcanoes that are in the ocean, through mid-ocean ridges, and also the effects of sediment diagenesis. That might affect the concentration in the ocean as well as small amounts. But really the rates of these processes, even volcanic emissions, are very, very small compared to the fluxes of carbon and oxygen into and out of the surface layer of the ocean by the processes up there of these guys, of the photosynthesis, respiration, decomposition. These are the most important of all of the processes. So yeah. This is a table of some of these that summarizes some of these processes. So, for instance, photosynthesis increases the concentration of oxygen, reduces the CO2. You have this table in your notes. I'm not going to read it out in the lecture, but I mean you can look at it and maybe remember some of it, hopefully. So, looking at oxygen now. So, if we think about these processes, first of all, the very, very surface ocean, at the very top, the concentration of oxygen in the surface of the ocean is determined by how much oxygen there is in the atmosphere, okay, which is going to be kind of 21%, and the temperature and salinity of the water. Okay, so that will determine how much oxygen we can actually get into the surface layer of the ocean. And then just below the surface, okay, we'll be having some phytoplankton living. Actually, so if you go to the discussion forum online, there's a diagram of basically of a profile down through the water column that shows actually the maximum rate of photosynthesis is not at the surface of the ocean where all the light is. It's a little bit below there. Okay? So one of the questions that I've posed on the discussion forum is actually why is that? Why isn't photosynthesis highest at the surface of the ocean? Why is it at kind of maybe 100 meters depth? 100 to 50 meters depth. So have a think about that and post some answers on the discussion forum. It'll be fun. But you can see just below the surface there's this slight increase in concentration. Okay, just kind of up here. Okay, so it's higher than it would be if it was just in equilibrium in the atmosphere, and that's largely because of this process of photosynthesis. We're producing oxygen. Then as we go down into the ocean, we have a region where there's a low oxygen concentration, and that's because this is where respiration of all of the organic material that's formed in the surface ocean, that's sunk down and is being kind of broken down, it's being respired, and that is using up any dissolved oxygen in that water. Okay? And it can't be replenished because it can't mix up to the surface, okay, because it's down here at a kilometer depth. So that explains the concentration profile. In the very deep ocean, we'll come on to this in a few more slides, but this is a mixture of water that's basically been advected from the surface a long time ago and is now in the deep ocean, is being slowly circulating around, and the oxygen concentration is gradually increasing in that water mass. So that's this process of advection is determining what goes on in the deep ocean. Okay? So this is a real measured profile of oxygen concentration in the Atlantic Ocean. So this is Portugal here. So this is a cruise that I went on a couple of years ago. Okay, so you can see on here there are a bunch of processes going on that are changing the oxygen concentration. I should just point out that I've broken the scale here. So I've zoomed in over the top 100 meters or so of the profile, and then the scale is slightly condensed, going down to 4 kilometers. So you can see at the surface, the oxygen concentration is a little bit lower than it is at 50 to 60 meters. Okay, so this zone here where photosynthesis is going on, so process B is photosynthesis. Feel free to write that in. It will be a good thing for you to learn. Yeah, good thing to learn. equilibrium with the atmosphere by Henry's law at the top. We're respiring all of the organic material at C here, and D is where we've advected the deep water from somewhere else that had a higher oxygen concentration. Okay, and just to point out, so you can see here that this is the measurement of the fluorescence in the water, so how green it is, basically, or how much fluoresces when you shine light on it. So you can see all of the phytoplankton are actually concentrated down here, around 60 meters, and not up at the surface. Okay, so that's got implications for if we wanted to look at photosynthesis using remote sensing. This is the only part of the ocean we can see from space, whereas all of the activity is going on down here. Okay, that's a little aside, really. So if we look at the surface oxygen concentrations, again, so I mentioned this is determined by the temperature and the salinity of the water and the exchange with the atmosphere. So you can see that the dissolved oxygen concentration is very much, okay, following where the temperature is. So where it's cold in the polar regions, we have higher oxygen concentrations because the water is colder, can absorb more oxygen, and is warm, and there's less oxygen in the tropics. So that's basically another view of that same map up there on the top left. And what these other maps are, we're basically just taking slices down through the ocean at 100 meters depth, 300 meters depths, and 1,000 meters depth. So you can see there are basically that depletion of oxygen as you go down in the water column, okay, that is not spatially uniform. Okay? So this is that zone C where we're respiring all of this organic material once it's been produced in the surface layer. Okay? And you can see that there are zones of the ocean, particularly underneath these regions where we had lots of upwelling. Okay, you might remember from previous lectures. So these regions have got a lot of biological material being produced, therefore there's a lot being respired at depth. So these are regions that the oxygen concentrations, in fact, get so low, so this contour here of a concentration of 0.45 milliliters of oxygen per litre, this is a kind of a sort of somewhat arbitrary threshold below which macrofauna, so fish and things that like to breathe oxygen, well, not breathe, but I guess fish kind of breathe water, anyway, through gills. They can't survive in that zone, okay? The oxygen concentrations are too low. So these are sometimes referred to as dead zones in the oceans, or oxygen minimum zones. Oxygen minimum zones, OMZ is one of these TLAs, three-letter acronyms that you quite often hear bandied about in chemical oceanography. And you can see that these regions are quite expansive. And actually, going forward into the future through climate change, as the oceans get warmer, the oceans get more stratified, and we increase productivity in these regions, these dead zones are increasing in size. Okay, so this is this process of we're basically taking organic material and oxygen that's dissolved in the water, and we're decomposing it back into these forms here. So we're releasing nutrients into the water in these oxygen minimum zones, but we're taking away oxygen. Okay, and these are basically underneath these zones we have upwelling along the equator, along coasts. And if you were here for the vampire squid video, this is the kind of place where this guy lives. So in this oxygen minimum zone, there's incredibly low oxygen concentrations. So organisms have adapted. I mean, these oxygen minimum zones have existed throughout all of geological time. Anywhere we have lots of productivity in the water column, we tend to get these oxygen minimum zones. So these organisms, like the vampire squid, have adapted their physiology to survive in these zones. So they've got very low metabolism. They've got all kinds of kind of bio-adaptations to living this minimum zone. Okay. So the problem is that sometimes we might get a storm that might cause lots of upwelling, and that will bring this water that's got no oxygen, okay, up onto the continental shelf, and bad times for all of the things that are living on that continental shelf, because they are not adapted to living in this low oxygen environment. They very much die, which is bad for them, because they need this, and this has been removed from the water, that lovely, lovely oxygen. Okay, so So this is kind of relevant now to the practical, which some of you did yesterday, some of you will be doing next week. So you can see now in the deep ocean, so this is now going even deeper, so we're now at 3,500 meters, we're basically taking surface water that has a very high oxygen concentration, because deep water in the present day is currently forming in regions around the world in the North Atlantic and around Antarctica, which are very cold regions. So they can absorb lots of oxygen. That water sinks down to the bottom of the ocean, and then as it moves around the ocean, it's gradually decreasing in its nutrients, in its oxygen, as organic material is constantly raining down in that marine snow into the deep water and is being respired and oxygen is being used up. Okay, so we can use that kind of like to track around the deep ocean. We can track, match up our increases in nutrients as we flow around the ocean, as nutrients are being remineralized from the organic matter, with the increase in oxygen. So the two should be paired together. Okay, and we can kind of see that in these kind of maps now. So as we are decreasing in oxygen content as we go around this global conveyor of ocean circulation, we can see that the nutrients are increasing. So the nutrient cycles and the oxygen cycle within the ocean are really closely linked. Okay, so we're going to move on from oxygen now and talk about carbon. So this is an old figure now from a very, very old IPCC report, but effectively it shows it quite nicely that we can divide up the ocean and the atmosphere into a series of boxes where we consider where all the carbon is. So these numbers are now very, very wrong in terms of there's now much more carbon in the atmosphere than when this figure was produced. But the atmosphere has got some carbon in it in the form of carbon dioxide. The biosphere has got some, we're burning lots of fossil fuels and all that kind of stuff. But the ocean has got a huge amount of carbon dioxide stored in it. And it's also got a huge amount of carbon stored into it. And that is proportioned between the surface ocean and the deep ocean, okay, because these can be considered as separate boxes when we're thinking about carbon and also thinking about nutrients and anything in the ocean, because the surface layer of the ocean is so well separated from the rest of the ocean through its kind of buoyanciness, because the ocean is heated from the top, okay, by the sun, so it stays warm and buoyant. There is some fluxes in between the dissolved carbon forms and organic forms, and that's largely what is responsible for this increase into the deep ocean over long timescales. So the other thing that's important is actually it's not just carbon dioxide dissolving in the water. There's a series of chemical reactions that go on that are equilibrium reactions. So the first one is the reaction of dissolution, and that's at the top here. So we take carbon dioxide gas and we actually dissolve that gas in the water to form aqueous carbon dioxide. And that's an equilibrium reaction that goes backwards and forwards, so gas will exsolve out of the water back into the atmosphere constantly. So this reaction goes backwards and forwards, backwards and forwards. And the equilibrium position of this atmosphere, of this equation, is what determines how soluble carbon dioxide is in water. Okay, so that's the thing that's dependent on temperature and salinity. But once you've formed that aqueous carbon dioxide, it doesn't just sit there as carbon dioxide in the water. Some of it reacts with the water. So it doesn't just dissolve, it reacts. And that reaction forms this compound here, H2CO3, which is carbonic acid, which is an acid, very much like nucleic acid. So this, again, is an equilibrium reaction. It goes kind of backwards and forwards, backwards and forwards. So we reach an equilibrium position where we have some CO2 aqueous and we have some carbonic acid in solution. Now, this carbonic acid molecule is extremely unstable. Okay, so it doesn't really hang around much in the ocean. There's actually a very low concentration of it. But it doesn't just convert back to CO2 and water. It actually spontaneously breaks apart. It loses one of these hydrogens and becomes the bicarbonate ion, so HCO3 minus, and hydrogen ion, which then, again, that molecule is spontaneously can break apart into the carbonate ion, which is CO3 2 minus, releasing another hydrogen ion. So that means that the total amount of carbon dissolved in the ocean is actually a sum of all of these different carbon-bearing species. Now, actually, so it turns out that this compound, the carbonic acid, is actually so unstable we can almost ignore it, and we can just consider that the total amount of concentration of carbon dioxide dissolved is equal to the carbon dioxide plus the carbonic acid. So we have this term, dissolved inorganic carbon, that is the sum of CO2 plus bicarbonate and carbonate ion. So it's all of these three different chemical species, and it turns out that most of the carbon is in this form, the bicarbonate. So about 90% of it is that. 9% of it is carbonate ion, and only 1% is actually still as dissolved CO2. So that means that we can dissolve CO2 from the atmosphere, okay, and the atmospheric concentration of carbon dioxide will stay relatively low, but we can store lots of carbon in the ocean in these other forms which are not able to exchange with the atmosphere. Okay? So the fact that only one of them can exchange with the atmosphere, only the CO2, is really important because that allows us to store lots of carbon in the ocean. Okay, so just to talk a little bit about pH. So this again was in the introductory video, but pH is just a measure of the acidity of a solution, or essentially a measure of the power of or the availability of hydrogen ions. So it's a negative logarithmic scale. So a pH of 1 has 10 to the minus 1 moles of hydrogen ions, whereas a pH of 7 is 10 to the minus 7 moles of hydrogen. So every time you go down 1 pH unit, so every time you go up 1 pH unit, you reduce the concentration or the activity, we can think of activity as concentration in this case, of hydrogen ions by a factor of 10. Okay? So a pH of 8 is 10 times less acidic than a pH of 7. Okay, so we can think now about how this acidity of the ocean matters, because if we, for instance, just look at now that these equilibrium reactions have got hydrogen ions in them. Okay? So if we add hydrogen ions, if we make the ocean more acidic, okay, that means that we're basically adding things to this side of these reactions. That forces the equilibrium point over to the other side. Those hydrogen ions basically get used up in these backwards reactions. So if we add hydrogen ions, we acidify the ocean, we lower its pH, we're going to change this proportion of carbonate ion to bicarbonate ion to CO2, so we'll end up having less of this, a little bit less of this, and more of this. Okay? We're moving everything over to the left-hand side of the reactions. So this is really important, okay, because acidifying the ocean will therefore have an impact of how much carbon we can store in the ocean, because the more we move things over to the left-hand side of these reactions, the greater the proportion of the total carbon will be able to exchange with the atmosphere. Okay? So if we suddenly completely acidified the ocean and turned all of these carbon species into CO2, all of that CO2, all that carbon in the atmosphere would be able to interact with the atmosphere. And instead of the atmosphere having kind of 600 gigatons of carbon in, it would have 40,000 gigatons of carbon in. And that would be extremely bad. I mean, that would make the planet completely uninhabitable. It would get so warm that water would boil. It would be very, very bad. So let's not do that. So this is that proportionation between the different species expressed as a function of pH. So this is the basic side of the scale. This is the acidic side of the scale. Okay, so pH is increasing this way. And we can see at low pH, okay, if we completely acidify the ocean, all of the carbon would be a CO2. This little star here just means CO2 plus the carbonic acid species. Whereas if we completely made the ocean basic, okay, then all of the carbon would be as this carbonate ion, and that would be fine, and we could store loads and loads of carbon in the ocean. The actual pH of the ocean is around here, around 8.1, where most of the carbon is in this bicarbonate form. We've got a little bit in carbonate, and a tiny amount is a CO2. So if we change our pH by a little bit, we're going to start to come up this slope of increasing the proportion that is CO2 quite dramatically, and that would be super bad for how much carbon could exchange back with the atmosphere. Okay, so what happens if we just add carbon dioxide to the ocean? So if we were adding carbon dioxide by, say, fossil fuel burning, what effect does that have on acidity? So if we follow those, I've just written out those three equilibrium reactions as basically following each other now. So going from CO2 to water to carbonic acid to the bicarbonate, not put the next one on. But you can see that if we add CO2 by just adding CO2 to the atmosphere, which then ultimately dissolves in the ocean, that would then force the reaction over to the right-hand side, okay, which would add hydrogen ions to the ocean. Okay? So adding CO2 to the atmosphere acidifies the ocean, which then will move this equilibrium over towards this side, towards lower pH, which would then mean that even more of this carbon that's already in the ocean would want to go back into the atmosphere. Okay? So it reinforces the rise in CO2. It's a positive feedback. So fortunately, this is not a runaway process. Okay? So if this was a runaway process, we'd kind of add CO2 to the atmosphere, we'd acidify the ocean. That would mean more CO2 would go into the atmosphere because a greater proportion of the carbon would be in the CO2 form, and that would acidify the ocean again. So that would lead to the atmospheric CO2 concentration just rocketing up. Now, fortunately, that doesn't happen because when we acidify the ocean, we do change this speciation, the relative proportions of the different carbon species. But if we, for instance, if we do make it acidic, we are able to convert one form of this carbon into another form of carbon, and that absorbs some of those extra hydrogen ions that we've created. So the carbonate system in the ocean has this thing called a buffering capacity, okay, which allows it to basically mediate changes in pH. So there's a buffering capacity of the dissolved inorganic carbon, but there's also a buffering capacity of carbonates that kind of form in the ocean. Okay, so if we take calcium and carbonate, okay, we are forming calcium carbonate. That's the formation of the shells of these organisms. So if we look at what that means in terms of these equilibria, forming calcium carbonate removes carbonate from this system. Okay? That means that we're taking away some of the reactions, so that means that these equilibrium will move over back to this side to try and make up for that. Okay, so if we take out this carbonate ion, we will then create carbonate ion to replace that. That will add acid to the ocean because we'll be creating more hydrogen ions. So precipitating calcium carbonate, forming calcium carbonate shells, acidifies the ocean. So the opposite of that would be dissolving calcium carbonate. So we take calcium carbonate and we maybe dissolve it with some of the acid that's dissolved in the ocean. That forms us some of these species on this side of the equation. So we're adding things onto our right-hand side of our equilibria. That means that those will react with the hydrogen ions and neutralize that acidification. So dissolving calcium carbonate, okay, dissolving corals, dissolving coccoliths, that helps the process of ocean acidification. So we've got two buffering systems. We've got the buffering systems of the dissolved carbon species that can act quite quickly. And then we've also got the buffering of the solid carbon in the ocean, the calcium carbonate, the calcite aragonite. If we can dissolve that, that will also mitigate the climate, mitigate the ocean acidification. Okay? So once again, this is basically explaining it on this diagram. If we are dissolving our calcium carbonate shells, we're adding this guy back into the mix, so that increases the proportion of the carbonate ion. It will raise the pH. Okay, just think of it as basically adding alkalinity to the ocean. So I've just mentioned the word alkalinity. So I was very careful when I was talking about the pH scale not to say acid and alkaline. Okay, it's acid and basic, Those are the two end members of the pH scale. Alkalinity is a subtly different concept. So if we look at all of the stuff that's dissolved in the ocean, so this is the sea salt composition, okay, here. And instead of representing it as like the mass of chlorine and the mass of sodium, I've just converted all of those into the moles of chlorine and the moles of sodium and moles of everything. So it changes the distribution slightly. But then if I think about actually which one of these are positive ions and which one of these are negative ions. Okay? So I plotted that up here. So you can see on this side we've got all of the negative ions and their charge. So the sum of the negative charge and the sum of the positive charge. So it kind of makes sense that we've got roughly half of each. Otherwise, when you put your hand in the ocean, you'd get an electric shock. Okay? And anybody who's put their hand in the ocean, that doesn't happen. But actually, if we look at this kind of, I've just plotted them up as a bar chart, so all the negative, the anions and the cations over here. If we actually zoom in, okay, at this top here, we can actually see that there's this slight mismatch. Okay, so we add up all of the anions and it comes to here, just above fluorine there, whereas there are more cations in the ocean than there are anions. Okay, that's a bit weird. Okay, so it turns out that something else must be making up this charge deficit. Okay, so there's some negative charge that's missing if we look at all of the salt ions. So where that charge actually comes from is referred to as this total alkalinity. And the things that make up this charge are things like this. Okay, so things like the carbonate ion, the bicarbonate ion, they're negatively charged. Okay, so they can make up this charge difference here. Now, the reason why I've excluded them from the salts in this case is because all of these compounds here have a chemistry which allow them to change kind of their type and have a different charge. So they can convert from one charge to another with reactions like this. So, for instance, the borate ion here, boron and some OHs, is a negatively charged ion, and that can react and form boric acid and water. And the thing is, each of these kind of reactions that involves one of these chemical species here changing its ionization state basically is because it's taking up a hydrogen ion. Okay, so this net charge deficit, this difference here, this is an amount of charge deficit in the ocean which can be used to neutralize the addition of acid. Okay, so if you have pure water and you put a tiny amount of hydrochloric acid in that pure water, you will have made something that has got kind of pH of 1 or something. It can be very acidic. But if you took, say, seawater that will start off with a similar pH, okay, and you put a small amount of acid in that, the pH might change a very small amount, but most of those acids, those H pluses, will react with some of these species making up the alkalinity, and the total acidic change will be buffered. So the alkalinity, so the sum of all of these kind of charge varying negative ions, or you can you can think about it in a slightly different way as thinking basically if we take all of the conservative ions and we basically add up their charge deficit, okay, because these quantities will be the same. This is the capacity of that water, the ocean in this case, to basically to soak up the addition of acid. So if you've got a high alkalinity, you can put lots of acid in the ocean and not a lot will happen, which is really fortunate because if we had a low alkalinity and we put some CO2 in the water, it would acidify very easily, okay, and we could then store much less CO2 in the water. So actually these species here form a large part of this alkalinity of the ocean. Okay, so it's this buffering capacity is basically a feature of the carbonate system. So if we think about some of the processes that are going on in the ocean now, so we've talked a lot already about photosynthesis and respiration. So photosynthesis will take out CO2. Respiration will add CO2. So it will lower the amount of carbon or raise the amount of carbon, and it will also change the pH of the ocean because we're going to be adding and subtracting hydrogen ions, but it won't have any impact on alkalinity. So it won't have any actually impact on the total ability of the ocean to take up acid, because when we add these components, which are part of alkalinity, we're also adding the acids. So they kind of cancel out in our sum of alkalinity. However, if we are doing a process where we're forming calcium carbonate, okay, if we form calcium carbonate, if we dissolve calcium carbonate in this case, we're doing a process which removes hydrogen ions, okay, which that will raise the pH, but it's also adding alkalinity back into the ocean. Okay, so we're taking out hydrogen ions and we're adding in the carbonate and bicarbonate, so that adds to the alkalinity of the ocean. So dissolving calcium carbonate is good because it raises the pH, means the ocean can store more CO2. It also increases the ability of the ocean to buffer any acidic change. So actually doing something like dissolving the Great Barrier Reef, okay, made of carbonate, if we dissolve that, that would mitigate ocean acidification, okay, it would keep the pH high. It would also increase the alkalinity, so it would increase the ocean's resilience to adding CO2 to the atmosphere. I'm not suggesting that we should dissolve the Great Barrier Reef, because it's quite nice. So this is a summary of all of these effects. So if we basically are, say, for instance, producing organic carbon through photosynthesis, we are going to lower the amount of CO2 in the water and therefore in the atmosphere, whereas if we respire, the amount of CO2 in the water and the atmosphere will go up. This will have, obviously, an effect on the pH, okay, because we're adding and taking away CO2, which reacts with water to form an acid. Obviously, will also affect the total amount of carbon in the ocean as well, if we're adding or taking away CO2. Whereas dissolution of calcium carbonate or precipitation of calcium carbonate has a different set of outcomes. So this is important because when we produce, say, a phytoplankton bloom in the ocean of maybe coccoliths, we'll be producing organic carbon, okay, but we'll also be producing calcium carbonate because that plankton will have calcium carbonate shells. So if we produce here, we maybe lower CO2 by producing organic carbon, but we'll raise CO2 because we're precipitating calcium carbonate shells. So the overall effect on climate of CO2 in the atmosphere depends on the ratio of organic matter production to production of inorganic carbon. Okay? So actually this is the idea of the Great Barrier Reef. We don't want to kill that, but that would kind of help. Shame. Again, so this is looking at this idea of the effect of this activity going on in the surface ocean. If we grow more algae, does that algae have a calcium carbonate shell associated with it? Because if it does, we're going to export CO2 in the organic fraction down into the deep ocean. But if we export calcium carbonate from here, we're going to lower the alkalinity. We're going to raise the carbon dioxide concentration, which will counteract the organic carbon burial. So actually, things like the nutrient inputs into the ocean are really important to determine not only how much carbon is is produced by plants, but also the ratio of carbon to inorganic carbon. Okay, so if we have nutrients that have maybe got lots of silicon in them, okay, we might promote diatom growth. So diatoms produce organic carbon, but do not produce calcium carbonate. So that means that if we did that, then our organic carbon pump would be very, very effective, whereas our inorganic carbon pump, which is removing alkalinity and therefore adding CO2 to the atmosphere, would be ineffective. Whereas if we had a situation where we weren't adding silicon to the surface ocean, we were just adding nitrate and phosphate and all of the other micronutrients, we might promote the growth of coccolithophores or forams, which produce organic carbon, but also produce calcium carbonate. So in that case, the effect of the carbon drawdown would be reduced, which would be bad. Okay, so it's really the efficiency of this pump is acting in opposite effects to the efficiency of the inorganic carbon pump. Okay, so the ratio of the two is really important for the impact of productivity changes on climate. Okay, because it determines where this pH of seawater lies. The more calcium carbonate we produce out of the ocean, the more alkalinity we're removing, so that the more acidic the oceans can get by adding CO2. Okay, so again, so this efficiency is dependent on whether we have organic carbon or inorganic carbon, because they have different impacts on CO2. Also, the efficiency of sinking is very important as well. So if the particles sink faster, they can get out of the surface ocean a lot more efficiently, and that draws down carbon from the atmosphere as well. So understanding the whole ecological community structure that takes very small bits of phytoplankton and converts those into big bits of sinking marine snow through kind of biological packaging is also important in determining the efficiency of the carbon pump. Okay, so just briefly, there's another carbon pump that helps remove CO2 from the atmosphere, okay? Because if we can make overall carbon dioxide more soluble in the ocean, that means that we can take more out of the atmosphere and put it into the ocean. And this is the effect of the solubility. So this is the Henry's law, again, the thing that I mentioned at the beginning of the lecture. So warmer and warmer temperatures, we can store less and less CO2 in the ocean because it's less soluble. So if we can make the whole ocean colder, we can put more CO2 in the ocean, therefore less will be in the atmosphere. So the opposite of that is happening at the moment. So we're making the planet warmer, okay, through greenhouse gas warming and all that kind of stuff. But we are then adding CO2 even more because we can't dissolve it in the ocean as well. Okay, so it's a feedback process on climate change. So we can kind of see that through geological time. So the blue is a proxy for the Earth's temperature measured in ice cores. So we can see when it was cold, okay, the concentration of CO2 in the atmosphere, also measured in ice cores, was also lower. And part of this difference is due to this feedback between having cold water able to store more CO2 in it. Okay? So part of it is the solubility pump, but also part of this change in CO2 through geological time is due to changes in the organic carbon pump and the inorganic carbon pump. These are affecting the atmospheric concentration of carbon dioxide on all kinds of timescales. Okay, so this is kind of just what I've said here. Also, if we basically put carbon in the deep ocean and allow that water to sit in the deep ocean for longer before it's upwelled to the surface, we can hold more carbon down in the deep ocean. So this is what's happening now. So this is the ocean acidification effect. So the red line is the concentration of carbon dioxide in the atmosphere. I'm sure you'll all be very familiar with that curve, the Keeling curve, measured in Hawaii. You can see that that's constantly increasing. We've got this annual cycle because of photosynthesis and respiration on land. But the thing that's important is this green curve here. So this is the pH of the ocean. And you can see that the amount of carbon dioxide dissolved in the ocean in blue is going up at the same kind of rate as that in the atmosphere because they're in equilibrium with each other. And that increase of CO2 in the water is causing this acidification. So it's breaking apart the CO2 into bicarbonate and carbonate ions, releasing hydrogen ions, which is lowering the pH. And although this only looks small, this only goes maybe from 8.1 to 8.06 or something like that, because it's a logarithmic scale, that's a huge change in the acidity of the ocean. Okay? And we'll see tomorrow what kind of impacts that might be having on some of the biology. So just to finish with, we're going to just look at an example of how we can use geological evidence of extreme events that have happened in the past as maybe a look into how the chemistry of the oceans might behave in the future. So this is now, over here, and this is 60 million years ago. Dinosaurs died around here. And this kind of like wiggling up and down here, these are glacial, interglacial cycles. Okay, so these are huge climate change swings. Okay, so this is using oxygen isotopes as a proxy for temperature and ice volume. Details of that not so important. But back here in the Paleocene and Eocene, the planet was a lot warmer than it is today. Okay, and the event that we're going to look at is this tiny little spike up here. So it was a time when we were going through a period of kind of gradual warming over millions of years, and then all of a sudden there's this sudden kind of kick up. It got a whole lot warmer over a very short space of time. And the reason for that warming is thought to be a sudden injection of CO2 into the ocean and/or atmosphere. And we can see this here in a marine core. So on the left here we've got the carbon isotopes of the carbonate that's preserved in this core here. You don't need to worry about too much of the details of this, but what these basically tell us is that we're basically adding a source of carbon to the ocean that's got a very negative isotopic composition, and that's kind of typical of carbon that's been either buried in kind of fossil fuels or in methane somewhere. And we can kind of do some kind of modeling to kind of figure out exactly how much that was. And it's a lot. It's a huge amount. It's kind of the order of the amounts that we're putting into the atmosphere at the moment. And you can kind of see the effect of that in the actual sediment core. Okay, so you've got kind of like light brown coloured sediment here and kind of light sediment up here. But at this event where we're adding this carbon to the system, the core goes very, very dark in colour. And that's because we've added CO2 to the system. That's acidified the ocean. Okay, and it's stopped calcium carbonate being produced. Calcium carbonate is white, so our sediment core no longer has any calcium carbonate in. So we've acidified the ocean, we've added CO2 to the system, it's causing the planet to get very warm. And the key thing is that over time, that system will recover as more and more carbonates from all around the world actually dissolve and raise the alkalinity back of the ocean back up to what it was before, and allow the CO2 to be stored back into the ocean again and back into sediments. And the key thing is that this event here happened 55 million years ago. We suddenly added lots of carbon to the atmosphere. That causes everything to dissolve. And these are just different cores at different depths of the ocean. Okay? So for the whole ocean to recover, it's taken 100,000 years. Okay? So that's the kind of timescale that the planet takes to heal itself after a sudden injection of carbon dioxide. So that's how long it will take the planet to recover from what we're doing to it today. So that's kind of depressing. We'll end on that today. So these are the kind of the summary of the things that hopefully you will get from either today's lecture or re-listening to today's lecture on the internet, which will be posted on soon. There's also a bunch of videos and stuff on the Learn site, which you should probably have a look at for this. And tomorrow we're going to look at the effect of some of these changes in CO2 and in nutrients on coral reefs. So that will be fun. And I'll see you guys then. If you've not signed in, please do so I can make sure that people who aren't here are okay with life in general. That would be great.